Imagine you're throwing a surprise party for the universe. You've planned everything meticulously, down to the last detail. You know exactly when the guest of honor, our understanding of the cosmos, is supposed to arrive. You've calculated its speed, its trajectory, and you're all set for the big reveal. But then, it shows up way earlier than you expected, bursting through the door while you're still setting up the decorations. That feeling of shock, confusion, and a little bit of excitement is exactly what astronomers are experiencing right now. For decades, we thought we had a pretty good handle on how our universe was growing, expanding outward since its explosive birth in the Big Bang. We had a model, a story that worked, but science, in its relentless pursuit of truth, loves to crash its own parties. And the guest who just upended the celebration is the James Webb Space Telescope, or JWST. With its powerful golden eye, it has peered into the depths of space and time, and it has sent back a message that has left cosmologists both baffled and thrilled. The message is simple. The universe isn't behaving the way we thought it should. The expansion we've been measuring for a century isn't as straightforward as our best theories predicted. It's like finding out the rulebook you've been using to play the game is missing a few crucial pages, and we're just now realizing it. This isn't a story of failure, but one of profound discovery. It's a moment that reminds us that the universe is under no obligation to make sense to us. Our job as scientists is to keep asking questions, to keep measuring, and to be ready to rewrite the story when the evidence demands it. The confirmation of this cosmic puzzle, known as the Hubble tension, isn't a setback. It's an invitation. It's the universe whispering a secret, telling us that there is something deeper, something more fundamental, and something more mysterious at play than we ever imagined. It's a sign that we are on the verge of a new chapter in our cosmic story. So, get ready. We are about to embark on a journey to understand this grand cosmic mystery. We'll look at the tools we built to explore it, the puzzle they've uncovered, and what it might mean for everything we thought we knew about our past, our present, and our future. This isn't just a problem for physicists in lab coats. It's a fundamental question about our place in the cosmos. The story of the universe just got a major plot twist, and we all have a front row seat to watch it unfold. The curtain is rising on a new era of cosmology, and the view is absolutely breathtaking. To understand this new cosmic drama, you first have to meet the stars of the show, our two greatest observatories in space, the Hubble Space Telescope and the James Webb Space Telescope. Think of them as a dynamic duo, a pair of celestial detectives solving the universe's greatest mysteries. The Hubble, launched way back in 1990, was our first major eye in the sky, orbiting just a few hundred miles above Earth. It was a revolutionary tool that fundamentally changed our view of the cosmos. Hubble sees the universe primarily in visible light, the same kind of light our own eyes see, along with a little bit of ultraviolet and near-infrared. It gave us breathtaking images of stellar nurseries, dying stars, and galaxies billions of light-years away. Hubble was the pioneer. It showed us the lay of the land, painting a detailed map of our cosmic neighborhood and beyond. It was like the first explorer to chart a new continent, revealing wonders no one had ever seen before. It helped us pin down the age of the universe and provided concrete evidence that its expansion was actually accelerating. But for all its power, Hubble has its limits. It can't see the very first stars and galaxies that formed in the early universe. Their light has been traveling for so long, over 13 billion years, that the expansion of space itself has stretched it out, shifting it from visible light into the infrared spectrum. This is where the James Webb Space Telescope comes in. Launched in 2021 and positioned 1 million miles from Earth, Webb is a master of infrared light. Think of it as having cosmic night vision goggles. Its giant golden honeycomb mirror is designed specifically to capture this faint, ancient, stretched-out light. Webb can pierce through the dense clouds of gas and dust that obscure Hubble's view, allowing it to see the cosmic dawn, the birth of the very first galaxies. It's not a replacement for Hubble, it's a successor, designed to answer the questions that Hubble's discoveries raised. They work in tandem, one showing us the now and the other showing us the then. Together, these two telescopes give us a powerful, multifaceted view of the universe. Hubble is the brilliant general practitioner who can diagnose a wide range of cosmic phenomena, from planets in our solar system to relatively nearby galaxies. Webb is the specialist, the expert in cosmic archaeology who can dig back to the universe's baby pictures. It's the combination of their perspectives, Hubble's view of the more recent universe and Webb's view of the ancient one, that has brought this new cosmic puzzle, the Hubble tension, into such sharp and undeniable focus. They are our two greatest tools for reading the autobiography of the cosmos. So, how do we know the universe is expanding in the first place? It's a concept that can be hard to wrap your head around. It's not like galaxies are flying through space like shrapnel from an explosion. Instead, space itself is stretching, carrying galaxies along with it for the ride. A simple way to picture this is to imagine baking a loaf of raisin bread. As the dough rises and expands, the raisins inside the bread all move away from each other. From the perspective of any single raisin, it looks like all the other raisins are rushing away from it. The farther away a raisin is, the faster it appears to be moving. This is exactly what we see in the cosmos. In the 1920s, Edwin Hubble, the man the telescope is named after, discovered that the farther away a galaxy is, the faster it's moving away from us. This relationship is described by a number called the Hubble constant. This constant isn't just some abstract figure, it's our cosmic speedometer. It tells us the rate at which the universe is expanding. Getting this number right is one of the most important goals in all of cosmology, because it underpins everything else. It helps us determine the age of the universe, its size, and its ultimate fate. If the expansion is fast, the universe is younger. If it's slow, the universe is older. To measure the Hubble constant, astronomers need two pieces of information for any given galaxy: how far away it is and how fast it's moving away from us. Measuring the speed is relatively easy. We do it by looking at the galaxy's light. As a galaxy moves away, the light waves it emits get stretched out, shifting toward the red end of the spectrum. This is called redshift, and it's similar to how the pitch of an ambulance siren drops as it moves away from you. The greater the redshift, the faster the galaxy is receding. The hard part is measuring the distance. How do you measure the distance to something that is millions or even billions of light years away? To do this, astronomers use what they call standard candles. These are celestial objects that have a known, consistent brightness. Imagine you're in a dark field and you see a single candle flame. You can't tell if it's a faint candle that's close by or a bright candle that's far away. But if you know that all candles of a certain type burn with exactly the same brightness, you can calculate the distance just by measuring how dim it appears. In space, our best standard candles are specific types of exploding stars, called type Ia supernovae, and pulsating stars called Cepheid variables. By finding these objects in distant galaxies, we can figure out how far away those galaxies are, and in turn, calculate the universe's expansion rate. Here's where our cosmic mystery really begins. For years, scientists have been refining their methods to measure the Hubble constant, our cosmic speedometer. And in doing so, they've developed two completely independent ways to calculate it. The problem is, these two methods give two different answers. This disagreement is what cosmologists call the Hubble tension, and it has become one of the biggest puzzles in modern science. It's not a small rounding error. The two values are different enough that they cannot both be right, at least not within our current understanding of the universe. It's like two trusted GPS systems giving you conflicting directions to the same destination. The first method is the one we just discussed, the local measurement. It involves looking at things in the relatively nearby universe, like those pulsating Cepheid stars and type Ia supernovae. Scientists, including a team led by Nobel laureate Adam Rees, have used the Hubble Space Telescope to make incredibly precise measurements of these standard candles in nearby galaxies. This method gives us a snapshot of how fast the universe is expanding today. After years of meticulous work, this method has consistently produced a higher value for the expansion rate, about 46 miles per second per megaparsec. A megaparsec is a cosmic unit of distance, roughly 3.26 million light-years. The second method looks at the universe in its infancy. It involves studying the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, a sea of radiation that fills all of space. It's a baby picture of the universe, taken when it was only about 380,000 years old. By studying the tiny temperature fluctuations in this ancient light, scientists can use our best theory of the cosmos, the standard model of cosmology, to predict how the universe should have evolved over the last 13.8 billion years. This prediction gives us a value for what the expansion rate should be today. and this method gives a lower value, about 41 miles per second per megaparsec. For a long time, many astronomers hoped this tension was just a result of measurement errors. Maybe our understanding of Cepheid stars wasn't quite right. Maybe there was dust obscuring our view, making things look farther away than they really were. Or perhaps our analysis of the CMB data had some hidden flaw. The hope was that as our telescopes and techniques got better, the two numbers would converge and the tension would simply disappear. The scientific community was holding its breath, waiting for a final, decisive measurement that would settle the debate once and for all. Everyone was looking to the new sheriff in town, the James Webb Space Telescope. Enter the James Webb Space Telescope, the most powerful observatory ever built. With its unparalleled sensitivity and its ability to see in crisp infrared light, Webb was poised to be the ultimate tiebreaker. It was designed to make the most precise measurements of those distant Cepheid stars ever attempted. Because it sees in infrared, Webb can peer through the cosmic dust that might have been fooling Hubble, giving us a cleaner, more reliable view. If the Hubble tension was just an illusion caused by measurement errors, Webb would be the one to prove it. The entire cosmology community was on the edge of its seat, waiting for the verdict. The team led by Adam Rees pointed Webb at the same galaxies where Hubble had measured Cepheid stars. The goal was to cross-check the old measurements with this new, more powerful instrument. If the discrepancy was due to, say, interference from other stars crowded around the Cepheids or misjudging the effects of interstellar dust, Webb's sharper vision would reveal it. The initial results began to stream in, and the suspense was, honestly, palpable. Would the new, more accurate measurements align with the predictions from the early universe? Would the tension finally be resolved, putting our cosmic model back on solid ground? The answer, delivered in late 2025, was a resounding and, well, shocking no. Webb's observations didn't resolve the tension at all. In fact, they confirmed it with even greater certainty. The new, ultra-precise measurements of the Cepheid stars perfectly matched the earlier measurements made by Hubble. This was a bombshell. The discrepancy wasn't a mistake. It wasn't a smudge on the lens or a miscalculation. Webb's data confirmed that the measurements of the local universe are solid. The universe really is expanding faster today than our models based on the early universe predict. The problem isn't in our telescopes, it's in our theories. This confirmation has sent shockwaves through the world of astrophysics. Adam Rees himself put it bluntly, if measurement errors are now off the table, then it's possible that we have misinterpreted the universe. The easy way out is gone. We can no longer hope that this is just a technical glitch that will be fixed with better data. The James Webb Space Telescope, the very instrument we built to solve the mystery, has instead looked us in the eye and told us the mystery is real. The universe is officially weirder than we thought, and our neat and tidy story of the cosmos has a gaping hole in it. So what does this all mean? This isn't just an academic squabble over a few numbers. The Hubble tension strikes at the very heart of our understanding of the universe. It puts our most successful and comprehensive theory of the cosmos, the Lambda CDM model, also known as the Standard Model of Cosmology, on trial. This model has been incredibly successful for decades. It's built upon the foundation of the Big Bang theory and incorporates just a few key ingredients: normal matter, dark matter, and dark energy. The Standard Model is the recipe book we've used to explain everything from the cosmic microwave background to the large-scale structure of galaxies. It's the story of our universe, beginning with a hot, dense state nearly 14 billion years ago, and expanding and cooling ever since. This model is what we use to connect the physics of the early universe to the state of the universe today. The fact that these two ends of the cosmic story don't line up suggests that there's a fundamental flaw in the narrative we've been telling ourselves. Something is missing from our cosmic recipe. It's important to clarify that this does not mean the Big Bang didn't happen. The evidence for the Big Bang, the expansion of the universe, the cosmic microwave background, the abundance of light elements, is overwhelming and not in question. What the Hubble tension does challenge is our understanding of what happened next. The Standard Model of Cosmology is our best attempt to describe the evolution of the universe after the Big Bang. The discrepancy implies that our model is either wrong or, more likely, incomplete. There might be a new character or a new plot point in the cosmic drama that we haven't accounted for. Think of it like being a detective investigating a case. You have evidence from the beginning of the story and evidence from the end of the story. Your theory is what connects the two. But if the evidence doesn't match up, it doesn't mean the crime didn't happen. It means your theory of how it happened is flawed. You're missing a piece of the puzzle. For cosmologists, the confirmation of the Hubble tension is that critical moment when the detective realizes their prime suspect has an alibi. It's time to go back to the drawing board and re-examine all the clues. If our current model is incomplete, what could be missing? This is where things get really exciting, pushing us into the realm of new and exotic physics. Scientists are now scrambling to come up with new ideas that could explain why the universe expanded at one rate in its youth, but is expanding faster than expected now. One popular idea is that there might have been a period of early dark energy. In our standard model, dark energy is a constant force that began to dominate the universe's expansion a few billion years ago. But what if there was another temporary form of dark energy that gave the early universe an extra kick for a while and then faded away? This early dark energy would have briefly accelerated the expansion after the Big Bang, which would change the conditions we measure in the cosmic microwave background. If we then use our old flawed model to interpret that CMB data, it would lead us to miscalculate the expansion rate today, creating the tension we observe. It's a tantalizing possibility because it would mean adding a brand new ingredient to our cosmic recipe. Another idea involves dark radiation, a new type of fast-moving, undiscovered particle that would have existed in the early universe alongside photons and neutrinos. These extra particles would have added more energy to the cosmic soup, altering its expansion history in just the right way. Other possibilities are even more mind-bending. Some physicists have proposed that dark matter might not be as simple as we thought. Perhaps it has some kind of interaction with other particles or forces that we haven't detected yet. Or maybe gravity itself behaves differently on cosmic scales than Einstein's theory of general relativity predicts. Modifying our theory of gravity is a radical step, but the Hubble tension is a radical problem that might require a radical solution. We could even be dealing with something called phantom dark energy, a hypothetical form of dark energy that grows stronger over time, which could lead to a future where the universe tears itself apart in a big rip. These are not just wild guesses. They are serious hypotheses that physicists are now developing into testable theories. The James Webb Space Telescope, along with other upcoming observatories, will be crucial in hunting for evidence that could support or rule out these new ideas. By making even more precise measurements of the distant universe, we might be able to see the subtle fingerprints of this new physics. The Hubble tension has opened a door, and on the other side is a whole new landscape of physical laws and cosmic components waiting to be discovered. It's a thrilling time to be a cosmologist, standing at the frontier of the known and the unknown. This whole episode with the Hubble tension is a perfect illustration of how science truly works. It's often portrayed as a straight line of progress, where we steadily accumulate facts until we arrive at the truth. But the reality is far more interesting and chaotic. Science is a messy human process of trial and error. It's a conversation, an argument with nature where we propose ideas and nature tells us if we're right or wrong. And sometimes, the most exciting answer we can get from nature is a firm no. Being wrong in science isn't a failure, it's an opportunity. It's the only way we make real breakthroughs. When a long-held theory starts to crack under the weight of new evidence, that's when the real fun begins. It's a sign that we're about to learn something new and profound. Think of the moment when observations of Mercury's orbit didn't quite match the predictions of Newton's theory of gravity. That tiny discrepancy wasn't swept under the rug. It was a clue that pointed the way to Einstein's revolutionary theory of general relativity, which completely changed our understanding of space, time, and gravity. The Hubble tension feels like one of those moments. It's a crack in the beautiful edifice of modern cosmology, and through that crack, a new light is beginning to shine. The story of Hubble and Webb also highlights the incredible power of our tools. We build these magnificent machines not just to confirm what we already know, but to challenge our assumptions. We sent Webb 1,000,000 miles into space, a daring feat of engineering, with the hope of solving a puzzle. Instead, it told us the puzzle is even deeper than we imagined. That is a spectacular success. It means our instruments are now so powerful that they can show us the limits of our own understanding. They are pushing us off the comfortable shores of the known world and into the stormy, uncharted waters of discovery. This is the spirit of exploration that drives humanity forward. We don't climb mountains just to see the view we expected. We climb them for the surprises, for the unexpected vistas that change our perspective forever. The James Webb Space Telescope is our generation's mountain. Its confirmation of the Hubble tension is not a crisis for cosmology, but a celebration of the scientific method itself. It's a testament to our willingness to question our deepest beliefs in the face of evidence, to admit when we've misinterpreted the universe, and to embrace the humbling, thrilling reality that there is always more to learn. So where do we go from here? The confirmation of the Hubble tension has thrown open the doors to a new frontier in cosmology. The immediate future will be a flurry of activity as theorists race to develop new models and observers design new ways to test them. The James Webb Space Telescope will remain at the forefront of this quest. It will continue to refine its measurements of the local expansion rate, pushing the precision to a level where even the most subtle deviations can be detected. It will also continue its primary mission of peering back to the cosmic dawn, searching for clues in the light of the first galaxies that might hint at the new physics at play. But Webb isn't the only player in the game. A new generation of ground-based and space-based observatories is coming online, each designed to map the universe in different ways. The Vera C. Rubin Observatory in Chile will conduct a decade-long survey of the sky, discovering thousands of new supernovae that can be used as standard candles. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will be able to map vast swaths of the universe with a field of view hundreds of times larger than Hubble's. These instruments will give us an unprecedented amount of data, creating a high-definition movie of the universe's evolution. What other surprises does the universe have in store for us? Beyond the Hubble tension, Webb is already revolutionizing other fields of astronomy. It has given us shockingly detailed views of planets in our own solar system, revealing unexpected atmospheric patterns on Saturn. It is peering into the hearts of dense stellar nurseries in our own Milky Way, revealing how massive stars are born. And of course, it is sniffing the atmospheres of distant exoplanets, searching for the chemical signatures of life. Could Webb be the telescope that finally answers the age-old question, are we alone? The journey of discovery is endless. Every time we answer one question, the universe presents us with 10 more. The Hubble tension is not an end, but a beginning. It's a cosmic cliffhanger that guarantees the next chapter of astronomy will be one of the most exciting yet. We live in a privileged moment in human history, armed with tools that allow us to read the story of the cosmos written in starlight. We don't know what we will find, and that is the most exciting part. The universe is whispering its secrets, and for the first time, we are truly beginning to listen. The adventure has just begun.